Pleased to introduce Dragan Milicic, who is our first speaker this afternoon. And you see the title of his talk, so Dragan, you're welcome.
Thank you. So first I would like to thank Ivan for inviting me to come to this very beautiful and pleasant place to talk. And I feel sorry that I have to leave tomorrow because I think if I will be speaking later at the conference, then I could use a lot of notation from Wilfred's talk and modify my slides, but unfortunately I couldn't edit them during lunch, so my notation will be slightly different than his. Okay, so let me start by just explaining the notation. So for me, this G naught will be connected real semi-simple E group with finite center, and K naught is a maximal compact subgroup of G naught. And P naught will be a maximum torus in K naught. And G, K, and P will be complexified Lie algebras of G naught, K naught, and P naught. And I will assume that G naught and K naught have equal rank. And this means, and was clear from Wilfred's lecture, that P naught is a compact Arcana subgroup of G naught. And under these conditions on the group G naught, I mean, this is why I need this condition. Under these conditions, the group G naught has discrete series, which appear again in Wilfred's lectures very explicitly in the case of SU 1, 1. So then I will denote by B a Borel subalgebra containing this Lie algebra P of P naught, and N is its nilpotent radical of this Borel. And if I have an irreducible Harishchandra module for G naught, and they were introduced and described by Wilfred, then I can, for that N, I can compute a corresponding Lie algebra homology, and I get, so these in each degree from 0 to the dimension of n, I get the vector space on which T naught acts. So this is a representation of T naught. And those representations of finite dimensional, I mean, this requires a proof, of course, and the proof will come out in a few minutes from geometric interpretation, although it can, in fact, can be also proved algebraically. So if R is the root system of G and T, and then the roots, of course, are in the linear dual T star T, and let R plus be the set of positive roots such that corresponding subspaces span N, and let me denote by rho the half sum of roots in our R plus, and also Wilfrid's lectures, I will denote by W the Weil group of that root system. Then, by a result of Castleman and Osborne, we can actually describe the n-homology of V more precisely. So it is a sum of subspaces which transform under the action of the group T0 in such a way that the differential of that action is given by the linear form W lambda plus rho. So basically, to calculate n-homology of this Harshchandra module, we just have to know the dimension of this eigenspace on the right.
What is lambda? Is that the infinitesimal character?
Lambda is the infinitesimal character. Yes, that's true. Because our module is irreducible, so it has an infinitesimal
And the
character.
sum is over with the length b, or no? Is there
No, I'm not saying, this is just a very naive statement. These are the only rates which can happen in n-homology. This is what Castleman-Osborne theorem says, that only these rates can appear.
This is not constants there. This is so general.
No, this is just completely
The
general.
answer to the first one.
Yeah. I mean, this is just a very, very simple fact from homology logic. So, the first line is related to Greg's comment. If G0 is compact and V is finite dimensional representation, then the precise result is the famous result of constant. And if V is a discrete series representation, then this is a result of Wilfrid's in his paper on L2 cohomology. Then Williams pointed out, he figured out that Schmidt's argument still works for so-called non-degenerate discrete series. It will become clear later what this actually means. And then for some class of n's, Mirkovich calculated these n-homologies, and Zorgel published a paper with a proof of the general result, but by his own admission that his published proof was incorrect, and his paper I find extremely confusing. So
I think it's important to say it's not just the proof that is incorrect, also the statement is almost contradictory.
yes,
The result is almost contradictory.
yeah, it says, so what I'm going to discuss today is a part of this project to understand all these results from some coherent point of view. And this is a joint project with Wilfrid. And it has two parts. One is algebraic and elementary, and the one I will talk about today is geometric, and it fits in the program of this conference. So I will talk only about geometric view of this, and it's not clear that for this last question, so the case of arbitrary limits of discrete series, this is the right way to look at this approach. Maybe it's it's better to look at it algebraically, but at least the history of the problem and the history of the results, I think, will be very clear when you see this geometric approach, and I think at least people who like B modules, I think at the end will be able to, in the middle of the night, reconstruct the proof and the result easily. So I learned about the problem from Wilfred, who actually, as I understand, the question was raised by Phil Griffiths, and the result is used by people who study Shimura varieties. This is a different story. I just want to discuss this as an illustration of application of geometric methods in solving a problem in representation theory. So the first thing I have to discuss briefly, and I hope I can help Wilfred a bit with this, is the D modules and the connection of D modules and representations, what he will have to talk about at some point. So I'll denote by U of G the enveloping algebra of G. Z of J is the center of U of G, Wilfred discussed today. And X will be the flag variety of G. So this is the variety of all Borel subalgebras of G. And I consider it as an algebraic variety with Zariski topology. So I will be doing all of this in algebraic category. This is very important for further development. So X is a smooth projective variety, and for any X in X, I will denote by B of X the corresponding, X is a Borel subalgebra, but to make notation reasonable, I will denote by B of X the corresponding Borel subalgebra in G. And let B be the vector subbundle of the trivial bundle over X, with fibers consisting of corresponding Borels. And then for each Borel, I can denote by n of x the commutator of b of x with itself. And n is the vector subbundle of this bundle of Borels, such that fibers over x are just the corresponding n of x. Then an elementary fact is that this vector bundle B mod n is trivial, so therefore it's of the form x cross h, and we call h an abstract Cartan algebra of G, and the reason for this is that if I look at an arbitrary Cartan subalgebra, it sits in a bunch of Borels, but if I fix a Borel, then I'm fixing a point in X, and then I have a map from the Cartan in the Borel, and in this Borel, I have a projection on the quotient B mod n, and I hit a point in this H. So basically for any Cartan, if we pick a Borel which contains it, it gives us an isomorphism between this Cartan and this abstract Cartan. So over each X, we get this isomorphism of a concrete Cartan with this abstract one, which is important when we want to transfer data from H to the various cartons is important in calculations. Yeah, so this is what I was just discussing a moment ago, that if I pick an X and I look at this carton sitting inside B of X, then we have a natural isomorphism of C with H, and the dual map from H star into C star is called specialization. And of course, as we have seen, okay, maybe I should postpone this comment till the next slide. So first of all, we can use this to transfer roots from these cartons to the abstract carton, and this gives us reduced root system sigma in H star, which is the specialization map corresponds to the root system of the pair GC. And we can pick a set of positive roots, sigma plus and sigma, such that the span of root subspaces for the corresponding positive root systems spans n of x. I am sorry again that I'm sure that Wilfried will use the opposite choice of the positive roots, but in the calculations I will be doing later, if I try again quickly to change all the choices of positive roots with the opposite positive roots, I will probably lose a lot of minuses and make all formulas incorrect. So anyway, this pair, sigma and sigma plus, is independent of the choice of x, and it calls sigma the abstract root system of G, and we can identify the Weil group W, which we had before, with this abstract Weil group of the root system sigma. Okay, so this was just, again, notation, but then, again, we get to this issue of Parishchandra homomorphism, that there is a natural homomorphism of the center of the interlocking algebra of G with a symmetric algebra of H, and it establishes an isomorphism of Z of G with the Weil group invariance in a symmetric algebra of H. This is exactly what was discussed by Wilfried at the end of his talk. And of course, we can view the symmetric algebra of H as invariant polynomial, as polynomials on H star. Therefore, the Weil group invariance in S of H, we can identify the W invariant polynomials of H star. So if I pick an orbit of the Weil group in H star, then I can look at the ideal in the center of the Z of G, which corresponds to all invariant polynomial vanishing on the orbit theta, and this gives us the parametrization of the space of maximal ideals in the center, and then we put that U theta is the quotient of the interlocking algebra of G by the ideal generated by the curve, by this ideal I theta in the center. And we know by M U theta the category of all U theta modules. So this is basically in the category of modules over interlocking algebra with the infinitesimal character corresponding to this orbit theta. So now we get really to geometry. So Beilinson and Bernstein, in their theory of localization of modules over n-homology algebras, what they did, they constructed a family, d lambda, of twisted sheaves of differential operators. So if I have a smooth algebraic variety, I can define a sheaf of differential operators on it. And the twisted sheaf of differential operators is a sheaf of algebras on X, which locally looks like differential operators, but not necessarily globally. So I will give you some examples in a moment. So they constructed such a family of twisted sheaves on X with an actual homomorphism of the n-homology algebra into global twisted differential operators, which induce isomorphisms of u theta with these global differential operators. So basically, they constructed sheaves of algebras on X such that global sections of these sheaves of algebras are our algebras u theta. And and of course you can do this for any lambda from that particular orbit theta of the algorithm. So now if you ever studied Sayre's paper on coherent algebraic modules, then you immediately get the idea how to proceed. We can look at the category of modules or modules or sheaves d lambda, and we assume that they're quasi-coherent. This is the reason why we need to work in an algebraic category. And we can define two functors. We can define the functor of global sections from n lambda, and we land in n u theta. And we can define also functor going in the opposite direction, called the localization functor, which is given just as a tensor product of v and d lambda over u theta. And those two functors, from completely elementary reasons, an adjoint pair of functors, and under certain conditions they define an equivalence of categories. And let me recall that result. So if I look at dual system of roots of sigma, then for dual root alpha and lambda in H, we say that lambda in H star is anti-dominant if alpha check on lambda is not a positive integer for any positive root alpha. And of course, it's saying that lambda in H star is regular if alpha check lambda is different from 0 for any alpha in sigma. And then the equivalence of categories theorem is that if lambda is in H star is anti-dominant and regular, then these two functors are described on the previous slides, quasi-inverse equivalences of categories. And this is, in some sense, a last generalization of Borel-Weil theorem, because in the case of Borel-Weil, if you look at this, you will have here, say, finite dimensional representations, and here you will have corresponding line numbers. And the whole point of this equivalence of categories is that you can look at a problem, say, on the representation theory side, and by the equivalence of categories, you can move it in the problem in the category of localized objects. These are sheaves of modules over the specific sheaf of differential operators d lambda, and there you can use the d-module theory to analyze the problem and solve it, and then you go back by factor global sections and you reinterpret the result. And this is basically what I'm going to do in our calculation of n-homology. So let me say a few words about n-homology in this setting. First of all, there is an elementary formula which follows from the definitions that if I look at localization, which is certain d-module, I can calculate its geometric fiber at the point. So I have some d lambda module, and Tx of V is Ox. This is structure sheaf of X. It's stored at the point X. Tensor. I'm sorry. This will be over this. So I look at Ox X mod maximal ideal of, the X. So this is isomorphic to C tensor over star with the star of this d-module fact. So this is the left side of our formula that we calculate geometric fiber of localization, and if you write down what this thing is and use the formula for localization, you easily can show that this is zero n-homology. So this is just V mod n of x V weight lambda plus rho, this weight subspace of this for any x in X. So now I want to reinterpret this formula and give you its generalization. So let me denote by V the Borel subgroup of int of G corresponding to B from, and this B is the B from the beginning of my column. So this is one of the Borels containing this torus B. And then we know that, so this fixed Borel acts on a flat variety in the orbits of Ruhr cells, and they're parameterized by the Weil group, and I will denote by CW the Ruhr cell attached to W in W. I will denote by L the length function of W, and again, one elementary fact is the dimension of the Ruhr cell is given by the length function applied to the element of the Weil group in W. And then I will denote that IW, the inclusion of CW in X, and I will also need this map pi W, which is a projection of the Ruhr cell to point. Then I can reinterpret interpret the above formula in a stupid way, because I take my localization and I look at the Bruchhaus cell corresponding to 1, so this is just a point cell, and I take the D-module inverse image factor and apply to this, and this D-module inverse image factor in the case of inclusion of the point corresponding to B to the flag variety is just calculating geometric fiber. So the formula at the bottom is just the simple rewrite of the formula at the top. And this formula can be generalized in the following way. So I want to have the formula for all components of n-homology which appears in my original problem. And what do? Now I have my flag variety X. On it I have this D module D lambda of V, the localization of the Harshchiner module V. And I can restrict it to Bruchhaus cell given by W. Of course, to make this work, I have to use fancy homological algebra because all these factors are not exact. I have to work in derived categories.
Just a comment. You're not using so far the G as a Harshchiner model. You just okay.
Yes, I don't think this is relevant at all. The fact that this is Harshchiner guarantees that we get something finite dimensional here. Yes, you're right.
Because I would like to see where it would work, because I would like to think about the
this is with grain of salt, this is completely general. I mean, the only issue you have to worry is the action of the, and this is why I'm in this setting, is the action of the group the complex stores.
Yeah.
So if you don't care about this, then everything is completely general. So let me just explain what's going on here. First, we have this localization D lambda of V, which is a D module, and this D module is in my M D lambda in a category of D modules. But I will embed this category into bounded derived category of D lambda modules. And then, so this is just the complex to this D module. I attach here a complex which is everywhere 0 except in degree 0 where we put localization module. Then I want to restrict this to my Bruchhaus cell. So Bruchhaus cell is an affine space, and if we analyze this, we see that the influence of this twist lambda disappears here, so we just get a sheaf of ordinary differential operators in CW when we do this restriction. And because the inverse image for D modules, but if we restrict the scalars to O modules, is sheaf theoretical O module inverse image. So it's basically tensoring. So it has left derived functors. So here I get left derived functors of inverse image of IW. And the resulting complex is bounded. And then, so this B in my formula is this, and then I have this restriction, and then I project this to a point, and what do I end up with? I end up with a bounded complex of D modules over a point. So this is the bounded complex of vector spaces. So the statement is that if I take cohomology of this complex of vector spaces in degree minus p, I get the p homology and homology of the module W and the component corresponding to weight W lambda plus rho. So this is exactly the generalization of the formula I had on previous slides. And this formula, in principle, allows you to calculate n-homology. It's not, in general, a very useful formula because, in general, these restrictions, so this inverse images and direct images of D modules, it's hard to calculate, but in some examples, this can be done quite easily. So let me start with the first example, which is not much, but it will tell us that we're on the right track. So let me look at the case when F is a finite dimensional representation with lowest weight lambda. Then it has infinitesimal character chi lambda minus rho because of the rho shift, and its localization at lambda minus rho is the line bundle or sheaf of sections of a line bundle called lambda. So this is again a form of Borel-Weil because global sections of whole lambda will give us back F by the equivalence of categories. Now if I take this whole lambda and I restrict it to Bruhat cell, then I will get just a structure sheaf on the Bruhat cell. This is, if you think about this, it will become completely obvious that this is the result in degree 0 and nothing in the other degrees. And then when I push it to a point, I'm basically calculating algebraic Deran of this OCW on the Bruhat cell because of the definition of direct image of D modules, shifted to the left by the length of element W, and so I get this formula over here. When I put all of this together, I get the following formula for this component of n-homology of F, and this is just the Constant's theorem. I get C if P is equal to the length of W, and I get 0 otherwise. Okay, so now I want to look at slightly in a harder problem, and I want to look at Wilfred's result about discrete series. So in this case, as in his talk, I have K, which is complexification of K naught, and it acts on X with finite and many orbits. And the main point, which is important for this, is that discrete series representations are attached to closed orbits of K and X in a particular way. So if I take any closed orbit of K, then on this closed orbit, which is just the flag variety of K, we get an equivariant connection which corresponds to the character lambda plus rho. And then I take this connection, I take its direct image with respect to the inclusion of closed orbit into X, and I get the standard module attached to the closed orbit corresponding to this connection tau. I'm sure that Wilfried will discuss this in detail in his lectures describing the classification of irreducible Harshchandra modules. This is a very special case of this. The standard module in this case is irreducible, so the problem of unique irreducible sum is non-existent in this case, because this is just this guy. So these are standard Harshchandra sheaves attached to these closed orbits, and the theorem is that localizations of discrete series with infinitesimal character chi lambda are exactly these standard Harshchandra sheaves. So if I take a point in the orbit Q, then I can look at the intersection of the corresponding Borel with K, and this is a Borel subalgebra of K. Therefore, this map from X in B of X intersected with K is an isomorphism of the closed orbit with the flag variety xk of K. So, if I pick the closed orbit, it's naturally isomorphic to a flag variety of the complexified maximal compact. And I will denote by B of K the subgroup of B corresponding to this Borel subalgebra. So we call a root compact if the root subspace corresponding to it is in our Lie algebra K, and compact roots form a root system of the root system R, and we denote by WK the corresponding Weil group of K, which is generated by compact reflections, and by L of K is the length function of WK. And again, for any element of WK, we have a corresponding Bruhat cell, which is the orbit of P of K in X of K, corresponding to this W. And then, of course, these Bruhat cells in flag variety of F of K give us the corresponding stratification by orbits, BK orbits of the orbit Q and the above isomorphism. On the other hand, if I pick W in the big Weil group and pick this orbit, closed orbit of K intersected with the big Bruchhaus cell of this W, then the intersection is dk invariant. Therefore, it's either empty or the union of these dk orbits in Q. And then there is this very simple geometric lemma which explains how does this intersection looks like. So there exists a unique element of the one group such that the intersection V, such that the intersection of this closed orbit with C of V is a point in Q, and any other intersection comes from Bruchhaus cells CWV when W is in WK with Q, and this gives us the precise description of this intersection. So if we remember what our formula says, we have this D module. In this case, we have some Q, which is a closed orbit of K, and then we take some connection on it, and we push it forward by D module direct image, and now we intersect it with the Bruchhaus cell, and we see which Bruchhaus cells intersect this non-trivially. And in this case, the intersection is something very simple, and there is a base change result in theory of D module. So it essentially tells us that if I take a direct image and restrict it under certain conditions up to certain shift discommutes with operation in the other way, so we can first restrict this connection to this intersection and then take direct image. Anyway, if you use base change and the previous result, then you get exactly the theorem of Schmidt from his paper with slightly different description of these P's. So n-homology pieces are non-zero only if for U's which are in this coset of the element V. Otherwise, the intersection is empty and we get nothing. And for any W in WK, if we calculate this, then we get exactly this result. Let me point out that, so this is the difference of dimensional flag varieties, and here what I have is the dimension of the big cell which intersect, and this is the dimension of the small cell, the cell in a compact, in a closed orbit Q, and then there is another copy of this. So there is a codimension of this big Bruchhaus cell and the intersection which is entering, and also the dimension of the small. And if you look at the formulas in Wilfried's paper and do some simple counting, you see that it's equivalent to this. And also, I mean, if you want an easy test, you can assume that the group is compact. Then, of course, Wilfried's result specializes to this is equal to 1, L is equal to L of K, and this is exactly Costin's formula. Okay, so now to proceed, we want to understand this. Right? We want to understand how these cohomology classes from where they come. And now we get to Greg's favorite topics from a long, long time ago. And this is Strauber's resolution, and I learned about this from Greg in 82, yes.
You want to know the exact date?
No. So basically, let me try to be kind of, I'm short on time. So basically, what's going on? We have this closed orbit, we have a Q which has a stratification by this orbits of small Borel of K, Bk, and this stratification is such that we can first on do the following thing. I mean, we can take O on one of these small Bruja cells in Q, and we can take their direct image to full flag variety. This is this JW lambda. So this is standard module attached to this intersection. And okay, we know with WKQ, the subset of WK consisted of elements of the length Q with respect to the length function of this WK. And then there is so-called Poisson resolution of the D module corresponding to discrete series, which is given by this JW lambdas, and W's go over all elements in WK, where the length is the dimension of Q minus P. And differentials basically are given explicitly. They're basically just taking residues along some Bruja cells of codimension 1 in the closure of the nuclear Bruja cell. And this resolution give of IQ tau gives us a resolution of in our case that lambda is say antidominant. The global sections of this resolution are isomorphic with this D of P with basically complex corresponding to our discrete series representation. So therefore we get a resolution of this discrete series representation by global sections of the Z modules, and this is by definition Trauber's resolution of discrete series V. I mean, just a side comment that my former student Vanya Milicic actually proved that the Trauber resolution is the same as Enright-Verwagen resolution of discrete series, what was the conjecture of Crowder or yours, I don't know. So that definitely it's in Craig's talk. Now, because the modules in Crowder's resolution also look very simple with respect to this geometric picture, we can calculate from our formula their n-homology. And their n-homology appears only in 1 degree, depending on this W, and we see that now it appears in degree, which is dimension of x minus the codimension of this intersection whole thing. So they all appear in the degree which is controlled by codimension only. So now if I want to find the n-homology of V, I can calculate it by looking at the hypercohomology of the Traube resolution of this complex V. If lambda is regular, then all these weights appearing in an homology of the elements in the Traube resolution are different. Therefore, if I look at E1 term of hypercohomology spectral sequence of the dot, then this spectral sequence collapses because it contains for each weight only one term. And this immediately implies Schmidt's theorem and also shows that each cohomology class in Schmidt's theorem corresponds exactly to one module in Traube resolution. Okay. Let me just go back and if I can make another comment, that if I look at the corresponding situation for Coston's theorem, then Traube resolution is nothing else than VGG resolution. And this, what we get from this, that each, this is a well-known fact, that each cohomology class in n-homology of finite dimensional representation comes from a corresponding term in VGG resolution. Okay, so this basically explains Wilfrid's theorem in terms of geometry, but now let me assume that lambda is still antidominant but singular. Then still the functor gamma is exact, and therefore Traube resolution is still a resolution of this limits of discrete series V. And since the n-homologies of each summon in Traube resolution are these modules JW lambda, then we can calculate what happens when lambda, so when we go from regular lambda to singular lambda using tensoring technique. And so if we do this, we get a spectral sequence of tensoring, and because n-homology is concentrated only in 1 degree, from that we get again that for after tensoring only, again we have only one one-dimensional contribution, 1 degree. So the same formula which holds in regular case for n-homology holds in singular case for any element in Traube resolution. So now if lambda is WK regular, then this means, remember, the elements in Traube resolutions are parameterized by the WK coset. So if lambda is WK regular, all the ways appearing in the calculation of n-homology are different. So the same argument as before will apply and will give us the formula for n-homology and its limits of discrete series. And this means that Schmidt's result will hold also in that case, and this was exactly what Williams claimed. So the proof of this is exactly the same because we just use the fact that the only thing which matters is a regularity with respect to WK. If WK lambda is not WK regular, the differentials can be non-trivial and the complex and the situation is murkier, but still we have a filtration of our complex with respect to this codimension, this difference. And if you look at these formulas, you will see that actually if codimension is constant for all the orbits appearing in intersection, then the spectral sequence for cohomology will collapse and in equal term. So, I mean, I think that the same statement holds in general. It collapses in E2 term, and there are the cohomology of the complex is sum of cohomologies of the complexes which correspond to each possible codimension which appears in this calculation. So it's, I mean, this can be made precise, but that's why I'm sorry, I'm already the time. So let me show you the just very brief discussion of the first non-trivial example of this calculation for this. So this is in the case of SU21 when K is GL2C, and in this case you have three families of discrete series: homomorphic, anti-homomorphic, and non-homomorphic. For homomorphic and anti-homomorphic, by a result of Mirkovich, this say the case I care about is lambda equals 0, where Schmidt's result, as I just proved, it doesn't apply. But so if lambda is equal to 0, Mirkovich's result, you get nothing in an homology. I mean, one can calculate this explicitly using the formulas I described, but I don't want to do this. So the only interesting situation is this non-homomorphic case for lambda equal to 0. In this case, actually the limit of discrete series representation is a spherical principal series representation too. And the flat variety XK, of course, is a Riemann sphere, and so Q comes from a Riemann sphere. This is a point, and this is C. And if we write down the Trauber resolution, we get that our discrete series is the kernel of this surjective morphism of this J to the other J. Our formulas tell us n-homology of these J modules, and from the long exact sequence of n-homology, we find the n-homology of this limits of discrete series representation. And the shocking thing is that this n-homology is non-zero, as you can see, and this result was discovered by Parallel by brutal computation. I mean, he just wrote down this spherical principal series representation and the action of the standard complex, and after long calculation, you get this result. Okay, I'm sorry for going over time, and I'll stop here.
Thank you very much for this very interesting talk. Anybody? Floor is open for comments, questions? So what about going to a rank? How far do you think realistic?
I mean, I don't think that it's so much question of ranks, it's the question that the only way, I mean, why this calculation is simple, because if you look at this closed orbit and intersection with the cell, this looks smooth. So you mean the standard module attached to closed orbits? Yeah, I mean, I didn't think about this, but you can probably say something. But in general, if you take a non-closed orbit, then the intersection will be a mess. And I mean, I look at some low-dimensional examples, and you can do some calculations, but I think that they become extremely complicated. So, I mean, this formula is useful just in some accidental cases where when the intersections are simple and you can do some calculation.
So there's also a different answer to the question here. Namely, you prove a result not necessarily only because you can prove it, but also because it's relevant for something. And in the equal rank case, this has to do with automorphic forms. That's why it's interesting. And of course, I mean, when you have not equal rank, let's say closed orbits, then yes, technically it becomes trickier, but there's no connection to automorphic forms. So it's also much less research to actually do it.
Well, I have something in mind, that's why I'm asking.
Sure.
But yes, thank you, guys. Thank you.
No, I think this is because my reason of looking at this, I couldn't understand. I mean, I could understand technically. I mean, Wilfred's argument is very clear and simple, but I just couldn't understand philosophically why the cohomology classes are parameterized by the coset of the small wild group, the WK. And I think from this argument, this becomes completely
this is Trauber.
Yeah, but this is just the fact that the only thing which matters are intersections with this closed orbit, which are just parameterized by this process. And yeah, I mean, Trauber is a nice way to see geometrically what the classes, particular classes are, but I'm talking even more trivial level. That's so. What are these intersections? So this is that these intersections are given by something very simple.
Wonderful, I think this is a great experience.
Right. So I'm not even sure how to formulate the question. Suppose instead of trying to calculate the n-homology explicitly, you look at the standard complex as an object in some derived category, and then you try to characterize that complex within the derived category. Does this give us anything different?
Give me which derived category. I mean, standard complex is okay. I don't know. Category n modules is something very hard to
The T action.
Yeah, I mean, you don't have T action, you don't have Castleman-Osborne. I mean, here, everything is just kind of...
No, but I mean, you can keep the T action in the derived category.
Sure, but I mean, it's... You see...
See, there's something called the Concevich's principle. That whenever you see a complex, you should not be tempted to take its homology. You should just...
Yes, but...
Just leave it alone. It's a complex. And that's it. So I never understood that principle. I'm just quoting Maxine.
I mean, my feeling is that, I mean, standard complex gives you an homology, but in a way, otherwise it's...
It doesn't give you anything.
Yeah, so for
It's not very helpful.
Carnival wants to construct polymorphic forms with this discrete series as the component at infinity, and he does that by actually having the n-homology, not some complex.
Oh, I believe that Cariola is not going to agree with me. I'm looking at it from...
Well, I mean, so for applications, I mean, so yes, I mean, sometimes you may just want to look at the derived category, but for applications, you actually want to know what the n-homology is.
Well, there's some sort of duality between applications and theory, as we know.
I mean, my feeling is that standard complexes is very useful for some calculations, but in a way, if you want to understand the big picture, you should look at these things as derived functors, and then it becomes kind of secondary issue how you actually compute this. I mean, all these causal type things are kind of very, I would say, still very mysterious. So if you have some idea how to put it in a proper framework, this would be very interesting. I think we always kind of do tedious computations with these things. I mean, it's not like Cousin complex, which is very simple to understand geometrically.
Okay, I think we can thank the speaker again.